Mihalis from Princeton, and he's going to talk about that title. So, the title again is
Thanks a lot for the introduction. I hope you can all hear me, because for various reasons I can't hear myself. So at any point I'm talking too softly, let me know. So my title is The Interior of Dynamical Vacuum Black Holes and Strong Cosmic Censorship Conjecture in General Relativity. Let me give an outline at the very beginning of what I hope to say. So I'll begin by introducing this strong cosmic censorship conjecture in general relativity. And this conjecture naturally falls out of comparison between, in some sense, the two most famous explicit solutions of the Einstein vacuum equations, Schwarzschild and Kerr. So I will review that very, very quickly without assuming that you know so much about them, and explain this conjecture, strong cosmic censorship. So the study of this in the past has mostly been in the context of simplified problems, in particular a linearized problem, and certainly toy models. So next talk about that. And the main result that I want to talk about in this talk, which will be joined with Jonathan Luke, from Cambridge. Is in some sense a definitive statement about this conjecture in the neighborhood of the curve. So I'll say that when we get there, and finally I'll say what's left. All right. So off we go on understanding the interior of black holes and strong cosmic censorship. So the first most famous family of explicit solutions to the Einstein vacuum equation is the so-called Schwarzschild family. So these were discovered in December 1915. They were actually published in January 1916. So we are celebrating the 100th anniversary of their publication. And this is an explicit family of spherically symmetric vacuum, so that's to say Vichy-flat spacetimes. I'm not going to write down the metric in local coordinates. I'm just going to describe its global geometry, and this understanding I should add took many years to really develop. So the modern way that we understand spacetime is it's the Cauchy evolution of asymptotically flat, two-ended Cauchy data. So it's traditional to depict this in what's known as a Penrose diagram. So in Penrose diagram, two sort of dimensions are suppressed. So this sigma, the asymptotically flat three-manifold with two asymptotically flat ends, and the spacetime is that which evolves, say, to the future from the data. And the properties that I want you to remember about the spacetime are the following. First of all, the spacetime is geodesically incomplete. And this, of course, in general relativity, has a fundamental interpretation in terms of observers. It means that there are some observers who only live for finite time. That's the first property. On the other hand, so that's in some sense a bad property. On the other hand, it at the same time has a very good property. And the good property is that future null infinity is complete. So that's to say there is a boundary at infinity. This corresponds to faraway observers in the radiation zone, and that boundary is complete. So that means those observers, they live forever. So there are some observers that only live for finite time, but faraway observers, they live forever. Moreover, you can look at the past of future null infinity, and that region of spacetime is bounded by something known as the event horizon, and beyond the event horizon, there is more of the spacetime. So that more of the spacetime, this region here, is known as the black hole. So exactly means that this region cannot communicate with observers. And it turns out that actually all observers who are incomplete, who only live for finite time, they necessarily enter the black hole. So those are the properties that I want you to remember about Schwarzschild, and let me add one more fundamental property. Not only so what happens to these observers gamma that enter the black hole and live for only finite time? It turns out that they approach asymptotically as their time approaches its final value, a curvature singularity at r equals 0. But it turns out that actually this curvature singularity is much more than just a curvature singularity. It is an essential singularity of the metric. So that's to say that the metric is inextendable beyond this boundary, even simply as a continuous metric. It's a continuous Lorentzian metric. And this actually has a certain physical interpretation in terms of this observer. That's to say, the observer doesn't just feel an infinite pinch, but it's actually torn apart by infinite tidal deformations. So what you should remember is that this is a very, very strong singularity. So actually this sort of geometric formulation of how singular this is a recent result of Yatsby's. All right, so that's Schwarzschild. Already motivated by Schwarzschild, I can just mention another big conjecture in this subject. So my talk will be about strong cosmic censorship, but there's another conjecture that I'll mention briefly, which is known as weak cosmic censorship. So let me just set this up as follows. So in the bad old days of general relativity, many people thought that this geodesic incompleteness property of Schwarzschild was pathological and was somehow related to the spherical symmetry of the solution. And it was thought that maybe if you perturbed away from spherical symmetry, then this would disappear. And this hope, if you want, was spectacularly falsified by Penrose's celebrated incompleteness theorem from 1965, which in particular shows that this is not the case, that if you perturb Schwarzschild's initial data and you solve the Cauchy problem, then again the Maxwell-Cauchy development is again geodesically incomplete. So that does not go away. So then when you look at Schwarzschild again, then, well, it has this nice completeness property on the other hand. Future null infinity, so far away observers, they do live forever. So you might hope that, well, maybe that property is stable. And whereas Penrose's incompleteness theorem has a nice one-paragraph proof, the question of whether the good property of Schwarzschild is stable is completely unknown, and this is conjecture. This is the conjecture known as weak cosmic censorship. So the conjecture is that for generic asymptotically flat vacuum initial data, that's to say all but an exceptional set in the moduli space of all initial data, then the resulting vacuum spacetime always has a complete future value. So heuristically, one other way of saying this is incomplete observers, they always have to enter black hole regions. But for various reasons, this is somehow the correct formulation. So let me just say that this is really completely open. The only setting that we even understand physically why this should be true is a certain toy model in spherical symmetry, the spherical symmetric Einstein scalar field system, where the analog of this conjecture has been proven to be true by Christodoulou. And he also proved the necessity of restricting to generic initial data. That's to say, he showed that there are somehow explicit solutions for this. All right, so this is a conjecture that you can already talk about from the point of view of Schwarzschild. But as I said at the very beginning, Schwarzschild, of course, does not come alone in the class of explicit solutions. It's merely a one-parameter subfamily of a larger two-parameter family of explicit solutions known as the Kerr family. So these were discovered much, much later, in 1963. They're algebraically much more subtle, and so the form of the metric is somehow more interesting. Again, I'm not going to show you the explicit form. I'm just going to describe the global geometry, and particularly those features that will be of relevance in this talk. So, first of all, the similarities to Schwarzschild. So, like Schwarzschild, it arises from asymptotically flat two-ended initial data, which represents the initial data. And again, like Schwarzschild, it is geodesically incomplete. More about incomplete observers later. But it has a boundary at infinity, future null infinity, which is complete. Okay. So faraway observers live forever. And again, like Schwarzschild, there's a so-called black hole region. So there's a sort of, not all of space-time communicates with future null infinity. So in particular, sort of this and this are the only regions of space-time that communicate to future null infinity. And all incomplete observers, they necessarily enter the boundary. So those are the similarities. But now the difference. So the difference is the following. Whereas in Schwarzschild, all observers who enter the black hole are destroyed by infinite tidal deformations. In Kerr, all observers who enter the black hole, they survive all the way to the boundary of the region determined by initial data. And in fact, the space-time is completely smooth at the boundary of the region determined by initial data. So it turns out that you can extend this solution beyond as a solution of the Einstein vacuum equations. But these extensions are no longer unique. So Penrose's theorem applied to Kerr is just telling you that this darker shaded region is geodesically incomplete. But the reason that that's geodesically incomplete is simply because, well, you could extend it to a larger manifold. Okay? In fact, you could extend it globally in the sense that all observers that were incomplete in the initial manifold can pass into the extension. So what happened? Why was this then the boundary of the region that was determined by initial data? Well, you can understand this in terms of the failure of the domain of dependence. So if you're a point beyond the darker shaded region and you follow backwards a characteristic, you will never intersect initial data. So for hyperbolic PD, that sort of tells you that the solution here will never be determined at that point. So in the Schwarzschild solution, we saw this very strong singularity that destroys everything. In the Kerr solution, so this boundary, I should say, is known as a Cauchy horizon. It's a horizon for the validity of the Cauchy problem. In the Kerr solution, inside the black hole, we encounter a Cauchy horizon, beyond which we can extend the solution, but it's no longer repeated. So you might ask which of these two situations are to be viewed more favorably. The situation of Schwarzschild, where observers are destroyed by infinite tidal deformations, or the situation of Kerr, where they can live another day in this extension. And certainly, from the point of view of the individual observer who enters the black hole, this situation is to be preferred. But from the point of view of the collective, that's to say, to the point of view of what we want for our physical theories, it turns out that the Schwarzschild situation is viewed to be preferable. And it's preferable because, okay, some observers indeed are torn to pieces, but the theory is completely deterministic. So there is no inconvenient observer gamma whose future is not determined by time. So because of that, actually the existence of the Kerr solution poses, if you want, a philosophical problem for general relativity. And one escape from that problem, and this escape was first put forth by Roger Penrose in the late 60s, and his formulation from 1972, is to essentially hope that the Kerr situation was a fluke. That's to say, the Kerr, what happened in Kerr was non-generic, was exceptional. And so he put forth what's known as strong cosmic censorship conjecture. And this conjecture says that, well, for generic asymptotically flat then the sort of solution spacetime that's uniquely determined by initial data cannot be extended to a larger one as a suitably regular Lorentzian. So in particular, it's clear a priori that you certainly have to put generic here because Kerr does not satisfy this. So somehow, if you want, this, the Kerr situation was so problematic that it was reasonable to hope that it was a few. So again, you should think this as sort of the conjecture of global uniqueness in general relativity, or the validity of Laplacian determinism. And actually, this weak cosmic censorship, you should really think of this as the conjecture of global existence in general relativity. I mean, of course, in view of Penrose's incompleteness theorem, you don't have geodesic completeness, but this is the type of completeness that you can still hope to have generically. So these, if you want, are the two very big conjectures of classical general relativity. Okay, so I motivated this conjecture from wishful thinking, but there's actually another reason that you can hope it's true beyond wishful thinking, and this was again first put forth by Penrose, and this is the celebrated blue shift instability. So Penrose noticed the following geometric optics phenomenon associated to the Cauchy horizon of the Kerr black hole. So the phenomenon is the following. So imagine you have two observers, A and B, and observer B stays outside of the black hole, whereas observer A crosses the black hole event horizon and then heads straight to this Cauchy horizon so as to go to the extension space. So imagine if observer B sends a signal to observer A at constant frequency. So remember, frequency means as observer B measures. Now, you have to get used to these sort of Penrose pictures. This is an observer who does not enter the black hole. So this observer lives forever. So the length of this curve is infinite. On the other hand, the length of this curve is finite. So if you think that this observer is sending infinitely many signals spaced at sort of time 1 as observer B measures it, then the sort of subsequent arrival times of the signal as observer A measures it, they get sort of closer and closer together. So in the language of the electromagnetic spectrum, the signal is infinitely blue shifted as observer A approaches his or her Cauchy horizon crossing. So, well, you might think that geometric optics is some high frequency limit for solutions of wave equations. The Einstein vacuum equations themselves linearize to some sort of wave equations. So you might think that this would be viewed by the Einstein equations as some sort of instability, and thus maybe for generic initial data, you could not have Cauchy horizons of the form in Kerr. So actually you can take this heuristic one step further, and people did. So of course, if indeed you look at a linear wave equation on a globally hyperbolic background, then there are general theorems you can prove. In particular, linear wave equation can never blow up in finite time, let's say at a point of the globally hyperbolic ABPD theory. So the worst thing that can happen is that it blows up asymptotically. So it blows up in some sense as you approach this Cauchy horizon. So a linear equation is the worst thing. But of course, if you thought of sort of the scalar field as a poor man's linearization of the Einstein equations, well, in the full nonlinear theory, you might imagine that once perturbations are growing, then nonlinear effects will start to dominate, and they will cause space-time to blow up in some way before you have the chance to attain this sort of null hypersurface which will be emerging from here. So, if you want, that would suggest that the sort of generic picture would indeed revert to Schwarzschild, where there is somehow a space-like singularity, so a singularity with this type of causality, and maybe which looks sort of like Schwarzschild singularity also, that's to say where the metric itself blows up in the sense that you have no continuous extension. Somehow many people pioneered this picture. In particular, this was also influenced by another sort of very well-known picture of generic singularities in general relativity due to Belinsky, Khalapikov, and Lifshitz, which in particular sort of said that generic singularities in general relativity are always sort of space-like and very, very strong. So this sort of gave rise to, if you want, the received version of strong cosmic censorship, which I want to call it the strong version of strong cosmic censorship, because unfortunately the conjecture is already called strong something. So for want of a better name, I'll call it very strong cosmic censorship, which says that for generic vacuum asymptotically flat initial data, then the part of the solution uniquely determined by initial data cannot be extended to the Lorentzian manifold. That was the usual strong cosmic censorship. And now I'm going to tell you in what way it cannot be extended, even with a metric assumed only continuous. Because again, what I said here was vague. That's a suitably vague. And moreover, let's also tag on, and the singularity can naturally be thought of as space. So this was really the sort of received understanding of strong cosmic censorship in the literature. So I'm going to call this formulation very strong cosmic censorship. All right. So this is the sort of the conjecture that I want to entertain in this talk. So let me begin by saying a bit what was done somehow in the past, even though some of the things that I'll talk about were actually done very, very recently. In some cases, very recent past. But actually the tradition of study of this problem in the settings that I'll talk about goes back since Penrose. So first of all, you might ask, is there some sort of rigorous theorem that demonstrates that there was something to Penrose's blue shift effect? And the answer is yes, and the most satisfactory statement actually can only be obtained in a sort of simpler cousin of the Kerr solution, which is so-called Weiser-Nordstrom solutions. So let me not talk about that specifically in this talk. You can sort of pretend, for the purpose of this theorem, that this is a result of Kerr. Say a little bit what you can say on Kerr. So on this sub-extremal Weiser-Nordstrom, then Jonathan Luke and Sungjin Oh proved recently that indeed, if you look at generic solutions of maybe I'll draw a picture. So this Penrose diagram of this poor man's cousin of Kerr has a similar causal structure. So their theorem is the following. If you consider generic initial data for the wave equation on this fixed spacetime with compact support initially, then the solution will fail to be in the local energy class at every point of the Cauchy horizon. So its energy will blow up there. So this formulation, which is maybe the most satisfying, as I said, you can only prove it in this sort of poor man's cousin, but you can prove something in Kerr which is almost as good, and this is also a recent result of mine with Jakob Schlappendorf-Rothman. So if you enlarge the class just a little bit to allow fast decaying polynomial tails initially, then the generic solution in this class on curve will have this problem. So, and I should say that sort of study of making rigorous formulations of this type of result goes back to students at Penrose back to work in this. So there's another result in this style which is actually maybe more satisfying than the one I just said for curve. So actually you can relate specific behavior on the event horizon of the solution of the wave equation with this blob. So if there's a lower bound for the decay rate on the event horizon, then you'll have this blob. And this is, again, a recent Jonathan Luke and Spears. So, okay, there certainly is something rigorous, there's something to the blue shift effect in linear theory, so keep this in mind. On the other hand, there's another result which in some sense is more unexpected. And this was proven a few years ago by Anne Franzen, and this result holds both on this poor man's version of Kerr, Meister-Ronster, but also on Kerr in the full subextreme range. And the statement is the following, that yes, okay, in view of the previous results, it can be that the local energy is infinite at every point of the Cauchy horizon. But the solution of the wave equation itself is uniformly bounded up to the Cauchy horizon, and in fact extends continuously via. That's a function. So for those of you who like extremal black holes, actually also last year Day and Gaich proved that this sort of type of theorem is also true in the extremal case. I guess in the Kerr case you have to assume axisymmetry. But in fact in the extremal case more is true. In particular, you can prove that the solution not only extends continuously, but you do not have blow-up of the local energy. So the extremal case turns out to be quite funny from this point. But anyway, that's only for experts. And there's also some recent result generalizing this theorem by Hintz and Bass. All right, so in some sense, at the linear level, at least at the sort of level of the scalar wave equation, one can understand the reality of the blue shift effect. On the other hand, one sees that it is not the amplitude of the wave that blows up; it is only the energy. This will be so now you can ask yourself the following question. Suppose we naively extrapolate the linear behavior of this sort of scalar wave equation onto the nonlinear Einstein vacuum equations. So that's to say, we identify our scalar field with the metric, so this should be G mean E. And the derivatives of C, we think of them as Christoffel symbols. Okay? And let's just pretend that the solutions of the Einstein vacuum equations, the generic ones near Kerr, behave precisely like solutions of the wave equation on fixed Kerr with this naive identification. This is very naive, but let's just pretend. Then what this would suggest is that the spacetime should indeed exist up to this null boundary. Okay, so the causal structure should not break down before. Moreover, you should be able to extend the metric, because the metric is C, continuously beyond this boundary. But the Christoffel symbols should not be square integrable around any point here. So in particular, the curvature should blow up, but more than that, somehow, in any regular coordinate system, the Christoffel symbols should fail to be this, if you want, would be a weakly singular boundary of space-time, which has been called in the literature a weak null singularity. So that's naive extrapolation of linear theory. And there was actually some evidence for this that sort of was suggested by a fully nonlinear spherically symmetric toy model that generalized the Einstein scalar field system of crystalline. And again, there was a long tradition of work on that by many, many people, and I worked on it a bit actually in my thesis a long time ago. So, okay, that's sort of one scenario. On the other hand, if you believe the original intuition, then in the absence of any symmetries and any toy models and linearization and all that, then the nonlinearities of the Einstein equations without symmetries, they should conspire to destroy this before it happens and create a much more singular space-like singularity. And somehow, even though there was a little bit of evidence, somehow, interestingly, the sort of the fully nonlinear but toy spherically symmetric model really came long before the linear theory without symmetry. But in any case, even though there was this evidence, this sort of really remained the received expectation. So this talk will discuss the question which of the two scenarios hold. So we'll leave these toys behind and go to the question of what do generic dynamical black holes look like. So one of the reasons actually that this notion of having such a singular boundary inside black holes was so repugnant is that somehow many people believed that just having a little piece of vacuum space-time, say this little piece here, bounded by a null singular boundary, would somehow be inconsistent. There are no explicit solutions of the Einstein vacuum equations in particular that have this type of singular boundary, just local. So many people thought that somehow these could not exist. So the first question you might ask is, can you create even a single example of such just a patch of vacuum spacetime which is bounded by a null boundary on which the Christoffel symbols sort of blow up, in fact fail to be square integrable, but the metric can be continuously extended beyond. And this problem was resolved in very nice work of Jonathan Luke. So he showed that indeed weak null singularities do exist, and you can create them by solving a characteristic initial value problem for the Einstein vacuum equations. So how does this characteristic initial value problem work? So Lydia in her talk yesterday talked about the Cauchy problem for the Einstein vacuum equations, and the characteristic initial value problem is a variant of that, where the data is posed not on a space-like hypersurface, but on two null hypersurfaces. So I'll draw the two null hypersurfaces like this. Okay, these are actually hypersurfaces. I only have one dimension. Left two-dimensional board, so I'll draw them like this. Okay. So there'll be initial data here and here, and you're trying to solve the equations to the future. And it turns out that initial data for the Einstein vacuum equations on characteristic hypersurfaces, it's actually easier, in some sense, some points of view. There's a trade-off, but from some points of view, it's easier to talk about the Cauchy data. It's really determined by geometrically the shear of this light column. And the shear is just the trace-free part of the second fundamental form of this light column. So this is denoted in the notation of Lydia's talk yesterday. You remember it as he. Okay, the letter he. And similarly here, the shear is denoted by he bar. So you essentially prescribe something at this sphere. So here, S2. You prescribe the shear here and the shear here, and you have data for the vacuum equations. So, in order to create a weak null singularity that's going to be coming from here, hopefully, you impose data. So I forgot my hat. So if you want, this he is the notation for the full second fundamental form, and the shear is trace-free part. So this is he hat, I should say. So actually, the trace is determined from this sort of shear and the information here by sort of integrating constraints. Okay. So you want to make. So remember, the shear itself. You should think of this as a Christoffel symbol. It's at the level of the second fundamental form. It's one derivative of the metric. So you want to make this not square integrable, but you want the metric to still be okay. So you want this to be integrable. Okay? So you can pick your favorite function which is integrable and not square integrable, for instance, this one. Okay, so I'm going to set this to be u bar equals 0. Okay? So these are constant u bar hypersurfaces. Okay. So you can give this initially this type of a profile. Okay. So this initially is not square integrable, but it's integrable. And okay, this is very singular, and so a priori, when you solve the Einstein equations, you're only going to be able to solve in some region like this. In fact, you can prove that for the generic quasi-linear wave equation, that's the sharp result for this type of data. But the Einstein equations are special, and Jonathan, in his theorem, proved that you can solve the equations in a full rectangular region like this. And then you look back, so you have this sort of limiting hypersurface, which is null. And it turns out that this profile of the behavior of the shear propagates, and thus this turns out to be a weak null singularity. So of course, as a physical example, this is quote artificial in the sense that you put in this data. On the other hand, it tells you that there is nothing inconsistent about having patches of vacuum spacetime with this boundary. So this is sort of a necessary precondition if you think that extrapolating the linear theory could be true. And maybe I should say something else. You might say that in this picture, now, if I'm going to believe that it might be possible to extrapolate the linear theory, that what about sort of this region here? Here it looks like I have two weak null singularities coming together, and nothing bad happens until they meet. So you might think that that's not possible, just a priori. And Jonathan actually showed that, well, that's also possible. So that's his second theorem. So he showed that, well, you can also give the sort of, let's call this the ingoing shear, the same type of singular profile. And you can choose the data otherwise to be small in such a way so that the solution lives in this whole rectangle. And now this is also a weak null singularity, and they meet. So it's not the case that something worse has to happen before they meet. So let me just say a few words about the proof of this. So the reason that this theorem can hold is because there's null structure in the Einstein vacuum equations. So there's special, the nonlinearities are special. They're not the worst that they could have been. They're special. But in order to identify that structure, you have to write down the equations in a clever way. And in fact, you have to somehow renormalize the sort of unknowns in the equations that you try to estimate. So in particular, Lydia's talk, she talked about the decomposition of the Riemann curvature tensor into null components, and there's a hierarchy of components which can be written like this. So these are the extremo components of the Riemann curvature tensor written in a null frame, and these are sort of the middle components, this hierarchy. And it turns out that these components are very, very singular. Well, this one on this side, this one on that side. It turns out, though, that you can rewrite the Einstein equations without reference to these components at all. So it's a very, very nice renormalization. You can trade them for considering the sort of Gaussian curvature of the spheres of intersection of these null curves. So it turns out that these components of curvature are still singular. In fact, they will not be locally square integrable, but you can put weights in your estimates. And the null structure of the equations is such that the sort of two bad components are never coupled together in the nonlinear terms. So it's really very remarkable how it all works out. Of course, null structure we know is essential for absolutely everything in general relativity, even just the stability of the Minkowski space. So it shouldn't be so surprising that it is the key here. But it's something very special about that. So all this is great. In particular, it says that principal null singularities and bifurcate null singularities can exist, but it doesn't tell you that they form dynamically in black hole interiors. So of course, if you want to understand what happens dynamically in black hole interiors, sort of by causality, you first have to understand what happens in black hole exteriors. In particular, you have to understand what happens at the event horizon. And well, it would be great to understand that. What do sort of generic solutions of the vacuum equation, even near initially Kerr spacetimes, what do they look like on their horizons? Do they even have event horizons? Do they have black holes in the sense that we're talking about? But of course, that's also an open problem in the subject, namely the nonlinear stability of the Kerr exterior. So it's conjectured that if you perturb Kerr initial data and you solve the Einstein equations, then the resulting spacetime will again have complete null infinity. So weak cosmic censorship will be true in the neighborhood of Kerr. And there will be the past of future null infinity will be bounded by event horizon, H+. And the solution, as you approach this point and this point of the Penrose diagram, will approach, settle down asymptotically to a nearby Kerr solution. And in fact, sufficiently fast polynomial So this is a conjecture. There's lots of work being done by many people on this problem in recent years, and hopefully this, maybe some restricted cases of this conjecture will be solved in the next. A few days ago I said 5 years. I'll say it again so people don't think I'm consistent. In the next 5 years. But in this talk, I'm going to assume the validity of this conjecture. I should add that as opposed to the cosmic censorship conjectures, this is a conjecture that everyone believes is true. There's no controversy surrounding whether this is finally going to be a true statement. So I'm going to believe this conjecture. So that's to say, I'm going to pretend that indeed everything I said is true. I'm going to erase the space-time in the exterior, and I'm going to start at the bifurcate event horizon, which satisfies the assumptions that supposedly come out of that conjecture. That's to say, I have a bifurcate event horizon which asymptotically settles down to a Kerr solution at a sufficiently fast inverse polynomial rate. And here also asymptotically settles down to a nearby Kerr solution at sufficiently fast polynomial rate. And I'm going to evolve the Einstein vacuum equations, and I'm going to ask, what does the development look like? Do you have a singularity like this, or does the development survive all the way to bifurcate out X? So the theorem, which will appear soon on the archive, which, as I said, is joined with Jonathan Luke in Cambridge, is the following. So we're in this setting. So suppose the stability of the Kerr exterior conjecture is indeed true. Then the entire Penrose diagram of Kerr is stable. So this is again the Penrose diagram. The spacetime lives all the way up to the bifurcate null Cauchy horizon, across which the solution is continuously extendable as a continuous Lorentzian metric. Now, I haven't said anything more about the regularity or lack thereof here, other than to say that this is a null bifurcate null hypersurface and the metric remains continuous. That is the statement of the theory. So in particular, if the stability of the Kerr exterior is true, which, as I said, we don't have a proof of this, but it's not controversial, that's sort of that's an expectation, then the very strong formulation of the strong cosmic tensor receives formulation as false, and it's already falsified by the neighborhood. So that is the theorem. Maybe I'll just say a little bit about the proof. So again, the initial data here is in some sense parameterized by the shears, and information actually that we think of as representing the final sphere here and here, which sort of encodes the parameters of the Kerr metric to which you're approaching. And here, so this is the things associated to these null directions I denote with the underline. So we're paying attention in Lydia's talk. This is, again, familiar. And so the assumption is that you have polynomial decay rates of this to 0 initially, and of this to 0. And so from the point of view of initial data, and this in some sense in natural coordinates corresponds to u equals infinity. This in some sense to u bar equals infinity. So from the point of view of initial data, it looks like you're trying to show a global existence theorem. And well, again, we know that the null condition is very important for sort of global existence. And the remarkable thing about this problem is, in some sense, it morphs as you approach this putative boundary. It morphs into a low regularity while posing this theorem. Because if you believe, this is not proven in a theorem, but if you believe that generically the solution is going to be singular here in regular coordinates, then in order to understand the solution in a neighborhood all the way up to here, you're going to have to be in the framework developed by Jonathan here. And it's remarkable that sort of the type of weighted estimates that respect the null condition and give you global existence with respect to this u that goes to infinity, they naturally merge into the type of weighted estimates that characterize this sort of singular behavior here. And of course, this is itself related to the blue shifter fractals. So, so in any case, just a little taste of what the argument looks like. So let me finish with what is left to be done on this problem. So in some sense, it's quite clear. Open problem 1 is to prove the stability of the Kerr exterior. If this is done, then in particular, definitive disproof of this very strong cosmic censorship will be a corollary of the above. So the second open problem, so as I said, I haven't told you that this boundary is singular. And of course, it will be quite bad if it's not singular at all, because it will really mean that observers, even for generic perturbations of Kerr, they can safely escape the domain of dependence of initial data without seeing anything locally bad happening. And then, well, theory doesn't say what happens, so they escape the bureaucracy of theory. So that would be very, very bad. We wouldn't want that about our physics. But as I said, even just extrapolating linear theory is suggestive of the fact that this boundary should indeed be singular at the level already of the Christoffel symbols. So open problem 2 is to prove that for generic perturbations, the Christoffel symbols will be singular here. In fact, they'll fail to be locally square integrable around any point of the Cauchy horizon. So it turns out that this extendability, or I should say inextendability notion, was first identified by Dimitris Christodoulou. And the relevance of fixating on the Christoffel symbols being locally square integrable is that that sort of is the weakest, traditional at least, notion of a weak solution of the Einstein equations. So if this open problem were true, then it would say that even though you can extend the solution as a Lorentzian metric, you cannot interpret any extension as a weak solution. So that would say that, in some sense, determinism for solutions of the Einstein equation is ensured, and maybe that's good enough. So in any case, I should add that some methods introduced in some of the work that I mentioned of Luke and Ho, and also Luke and Swirsky should be very useful in addressing this. So both of these open problems, I think, will eventually indeed be solved by rigorous mathematics. And so let me just say specifically that, so a corollary of the above would be that the Christodoulou formulation of strong cosmic censorship, that's where you say when inextendability means as a metric with locally square Christoffel symbols, is true in a neighborhood of the Kerr factor. Because, of course, to prove that a conjecture about generic solutions of the Einstein equation is false, it's sufficient to exhibit one open set in the motionless space for which it fails. But to show that it's true, you have to, it's really about generic solutions in the whole motion. So, of course, a full resolution in the affirmative of this version of strong censorship is probably never be done by rigorous mathematics. But this corollary is accessible. All right, thanks a lot.
Okay. Question? You talked about blow-up of energy in the original results. Is it the blow-up of these Christoffel symbols that you're talking about there?
Yeah, so that's in some sense it's exactly the translation of the naive extrapolation. So the energy of the scalar field is the local sort of L2 norm of the derivatives. So, and the Christoffel symbols are derivatives of the metric. So this is, in that sense, this is at the level of the energy of the gravitation field. Of course, I should add that there's a lot of structure in this blob. It's particular, it's not all of the Christoffel symbols that blow up. And this is related to the fact that the solution is actually regular in the tangential directions of the Cauchy horizon. So for instance, the easiest thing to say is, again, at the linear level, the scalar field. You can show that the derivatives which are tangential to the Cauchy horizon, they're actually smooth. So it's really only the transverse sort of null direction which characterizes
question? Okay, thank you very much.
So you don't get torn apart.
Wait.